So now we'll talk about the type of error that can happen during numerical computation. So before starting this part, I would like to show you some strange phenomena that you will find very strange if you don't understand how the computer represents the numbers. Let's take A as being some large number. Here it's 10 power 14. Okay. And let's write B equals A plus 0, 0, 1. Okay. And then I made C equals B minus A. So what I should get is C equals 0, 0, 1. But this is what I get. We are going to run this program and I get C equal 0. Strange, right? You may think there's a problem with MATLAB. No, my MATLAB works very good. Okay? Now I will delete 1, 0 and see what happens here. Still got 0. I will delete another 0. I get 0, 0, 2. So it's not exactly 0, 0, 1. I will delete again one more 0 here. And to see, I'm starting to get something close to 0, 0, 1. Not exactly still 0, 0, 1. I'll delete still another 0 here. Alright, now it's correct. Okay, so you can see that the error here diminishes when the number is smaller. There's two types of error that can happen during numerical computation. The first of it is the round-off error. So what you saw in the previous program was due to the round-off error in what we call the floating point representation. We'll talk about that. Now, the round-off error originates from the fact that we cannot represent a number with an infinite number of digits. So we can define the round-off error as being the difference between the real number and the represented number with a finite number of digits. So let's take an example in base 10, okay, because you are used to base 10, and in what we call the fixed point representation. Okay, so consider, for example, that we have 10 digits available to represent a real number in base 10. And for example, I will assign 1 digit for the sign of the number, and 4 digits for the whole part, and 5 digits for the fractional part. For example, if we have this real number here, okay, in this representation, because I have 5 only digits for the fractional part, okay, so I will consider only the 5 digits. And I will round these digits to the closer value, so 7 here. So if it was 6, 8, for example, it will be 8 here. Okay? And the round-off error is the difference between the two values. Now, the maximum round-off error in this representation is when we have here 5, 0, 0, 0, 0. Then here these digits will be or 8 or 7, and we will make a round-off error of 5, 10 minus 6. So this is the maximum round-off error in this representation. So as you can see here, the round-off error is fixed. It doesn't depend on how large the number it is. While in the MATLAB program where I showed you that the error depended on how large the number is. So in this, what we call representation, that we call fixed number representation, okay, the round-off error is fixed and doesn't depend on the number. Now the maximum number that we can represent would be 999.999, 10,000, and the minimum number is 0.0001110 minus 4. So this is what we call an example of a fixed point representation. Okay, so we assign a finite number of digits for the whole part, a finite number of digits for the fractional part. Okay, so in this representation, if the number of digits for the whole part is n1 and the number of digits for the fractional part is n2, then the maximum round-off error is 5 10 power n2 minus 1. Okay, because here I will have a 5. If here I have a 5000, then this is my maximum round-off error. Okay, so it's a fixed value, and the maximum number is 10 power n1, depends on the number of digits for the whole part, and the minimum number in absolute value is 10 minus n2, depends on the number of digits that we use for the fractional part. So the previous representation of a real number that we saw, which was the fixed point representation of a real number in base 10, permits to represent only a limited range of value. For example, if I want to represent a number as large as 10 power 100, I need 100 bits or 100 digits. I need 100 digits in base 10. Now, if the number is represented in binary, then I need much more digits. So another representation, which is more interesting, permits to represent a broader range of number with the same number of digits than the fixed point representation. So this representation is called the floating number representation. In this representation, any number can be expressed as x equals plus or minus a beta power n, where a is called the significant or the mantissa and n is the exponent. Now, beta is equal to 10 in base 10 and 2 in binary. For example, any number can be expressed in base 10 as 0 point some digits 10 power n. Now, in order to represent or encode the number, we only need these digits and the digits for the exponent. For example, I will give an example of floating point representation in base 10. So suppose we have 10 digits available to represent a real number in base 10. We'll use the following representation. We'll use 1 digit for the sign of the whole number, 1 digit for the sign of the exponent, 2 digits for the value of the exponent, or absolute value of the exponent, and 6 digits for the mantissa. So for example, the same number than before, if I want to encode it with this representation, I will represent it as follows. Now, here in this representation, I considered 6 digits for the mantissa. Okay? So this is just an example. Okay, so the number that I chose are arbitrary here. Now, in this representation, okay, I will retain here this 6 here first digits. I will round these digits, so 26 becomes here 3. Okay, and I will express the number as 0.45 okay, 2323, 10 power 5. Okay, and now, so these are my 10 digits, 1 digit for the sine, 6 digits here for the mantissa, 2 digits for the exponent, and 1 for the sine of the exponent. So in total, I have 10 digits. Now, the advantage of this representation, when we compare to the other one, is in this representation, for example, the maximum number that can be represented is 0.99999 10 power 99. And the minimum number that can be represented is 0.000001 10 power minus 99. So this is the minimum number in absolute value. Of course, the minimum number is when we have a minus here, minus sign. Okay. But now, let's see what happens to the round-off error. Now, in this case, if we use the floating number representation, the round-off error will depend on the value of the x. For example, if this is the representation, okay, of any number, where here x are any digits, okay. So the maximum round-off error here is when I have a 5 in this case, okay. So here I use 6 digits, so this would be 5 10 minus 7, this round-off error, multiplied by 10 power n. So the round-off error is 5 10 power n minus 7. So the larger is the number in a fixed point, in a floating point representation. So the larger is the number in a floating point representation, the larger is the round-off error. So in general, if you use n digits for the exponent, capital N digits, then the round-off error with this representation is 5 10 power n minus 1. Okay? Now you can understand now that if you want to calculate a very small number by subtracting very large number, then you will get a catastrophic error. Okay? Because the difference may be inferior to the round-off error. So now I'm going to introduce the binary representation, which is the representation that the computer uses to represent real numbers. Now the computer uses the floating number, the floating point binary representation. But in order to understand the floating point binary representation, we will first consider the fixed point binary representation. So in the fixed point binary representation, any numbers, any real number is expressed as a series of bits. The bits can take the value only 0 or 1. Okay? For example, if I have n1 bits for the whole parts and n2 bits for the fractional part, now I will name these bits for the whole part ai, with I going from 0 to n1 minus 1, if I have n bits, and the bits for the fractional part, bi, with I going from 1 till n2. And now if you want to convert this binary number into base 10 number, we just have to apply this formula. So the sum from I equals 0 till n1 minus 1 ai 2 power I, plus the sum from j equals 0 till n2 bj 2 power minus j. So this is the less significant bit for the whole part. This is the most significant bit for the whole part. And this is the most significant bit for the fractional part, and this is the less significant bit for the fractional part. For example, here, if I consider a 16-bit representation using 8 bits for the whole part and 8 bits for the fractional part. Now, this number would be 0 multiplied by 2 power 0, 0, plus 1 multiplied by 2 power 1, 2, plus 0, plus 1 multiplied by 2 power 4, 16. So it's 2 plus 16, it's equal 18. So this is for the whole part. Now for the fractional part, it would be 0 multiplied by 1/2 plus 1 multiplied by 1 over 4, which is 0.25, etc. So this number will give me 18.25. So this is the binary expression of 18.25. So this representation is equivalent to the fixed point representation in base 10, except that in base 10, okay, each digit can take a value between 0 and 9. Here, the digits can take only a value between only the two values 0 or 1. Now, the computer used only 32 bits or 64 bits to represent a number. The 32 bits representation is called single precision. The 64 bits representation is called double precision. Now, previously, the old computer used only 32 bits to represent a number. Now, the new computers use 64 bits to represent a given real number. Now, let's consider we have 32 bits, and if we allocate all these 32 bits only for the whole part, meaning we don't represent the fractions, even in this case, the maximum number would be 2 power 32 minus 1. So it would be 1, 1, 1, 1. Here you have, so this is 2 power 31, and this number plus 1 gives me 2 power 1, 0, 0, 0, 2 power 32. So this is 2 power 32 minus 1, this number. So, which gives in base 10 around 2.1 10 power 9. Now, in addition, if you want to allocate digits for the fractional part, this number will be further reduced. Now, for these reasons, we use the floating point representation. So, any number in binary can be represented as 1 point some fraction here, 2 power n. So, for example, the number 18.25 that we represented before in the fixed point binary representation. Now we can represent it in the floating point binary representation by considering the first non-zero digit that we find, and then we express it as 1.001001, 2 power 4, which is in this case the power of the first non-zero digit. Now, if you want to additionally to represent negative number, we can attach, for example, 1 bit for the sign, which is, for example, equal 0 when the number is positive and equal to 1 when the number is negative. So it's a convention. And we can do the same for the sign of the exponent. Now, any number, when we want to represent it in the floating number representation, so we have just to encode this part, the mantissa, and the exponent, and the value of the exponent in binary, and this would be enough to represent the number. So now I will give an example of a possible floating point representation in binary. This is just an example. So in this representation, I will consider one bit for the sign of the number. So this bit will be 0, for example, if the number is positive, and 1 if the number is negative. 8 bits for the exponent, and including one for the bit, one for the sign of 1 bit for the sign of the exponent, and 7 bits for the mantissa. So in the case that we have 7 bits for encoding the value of the exponent, the absolute value, so the maximum absolute value for the exponent will be 1, 1, 1, 1, 1, 1. So this is 2 power 8 minus 1 is 127. So this is the maximum value that the exponent can take in absolute value. Now if I want to have minus 127, for example, then I can attach a sign bit here, put a 1 here if the exponent is negative, or a 0 if the exponent is positive. Now the maximum number that you can represent with this representation is 1.111111 to power 127, and the minimum number will be when here it's 1.0000, when all the bits are 0, 2.2 power minus 27. Okay, so as you see, there's a huge difference. You can represent a large range of number. Now if I consider any given number that can be expressed as 1.xxxx to power n, the maximum round-off error for this number is when we have a 1 here. Okay, and so the maximum round-off error will be 2 power minus m, where m is where m is the total number of bits of the mantissa. So it will be 2 power minus m minus 1, so the value of this bit, multiplied by 2 power n. But for example here, where m equals 7, if the exponent becomes superior to 8, okay, then we cannot represent anymore the decimals. Now I will present the ITripleE standard that the computer used to represent real number in floating point representation. So first of all, we have 32 bits in total in this representation. Okay, 1 bit is allocated for the sign, 8 bits for the exponent, and 23 bits for the mantissa. The previous representation that we saw, we had also 8 bits for the exponent, and the minimum value for the exponent was minus 127. The maximum value was 127. So now here in this case, the minimum value is minus 126. Why? The difference comes that they use another representation for the exponent. Instead of assigning 1 bit for the sign of the exponent, they use another representation which is called the Bayes representation, and there's some bits that they use for representing the 0 and the infinity. Now I will not enter in these details, but what is important is to know that the minimum value is minus 126 and the maximum value is 127. So now with this representation, the maximum number will be 1.11111 to power 127. So approximately 2 power 128, which is 3.4 10 power 38. The minimum number would be 1.0002 power minus 126, which is approximately 1.17 10 power 38. And now the round-off error is 2 power n minus m minus 1, where n is the exponent for a given number x. So if you want to know what is the n for a given number x in base 10, just take the log 2 of this number. Okay, so the round-off error is 2 power n minus 24. So if you have a number for which the exponent is superior to 24, you will not be able to represent decimals for this number, because the round-off error becomes 1. Now for the 64-bit floating number representation, we use 1 bit for the sign of the number, 11 bit for the exponent, which can range between minus 1022 and 1023, and 52 bits for the mantis. Now, with this representation, the maximum number is 1.111, 2 power 1023, which is approximately 2 power 1024, which is 1.8 10 power 308. So, for example, now if I enter in MATLAB 2 power 1024, this will give me infinity. It will write inf, because it is superior to the maximum number the computer can represent. And the minimum number would be 1.0002 power minus 1022, which is 2.21 10 power minus 308. And the round-off error before, so it's 2 power n minus m minus 1, and in this case m equals 52, so it's 2 power n minus 53. So for n superior to 53, okay, x superior to 2.53, it's not possible anymore to represent decimals, because here the round-off error becomes 1. So now you can understand what happened in the beginning of this presentation. So when I took this large number and I add to it a small number, the small number was inferior to the precision, to the round-off error, so the number stayed the same, and that's why I got 0 for answer. Okay, so this is an important thing to know. When you subtract two large numbers, you can produce huge errors. Now I want you to write a program that verifies the maximum number and the minimum number that the computer can represent. For example, you can start by a number a equals 1 and then multiply by 2 till you reach infinity. So you can write a while loop while a different than inf, and count the number of steps that you multiply the number by 2. Okay, this will give you this number n, and it should be 1023 normally. And now for the smallest number, you divide by 2 till you reach 0. Another type of error that can happen during numerical computation is called the truncation error. So the truncation error results from the fact that we approximate in general a function by its Taylor series up to an order n. For example, this is the Taylor expansion for sinus x. Now if this sum goes to infinity, then this would give you the exact value for sinus x. But in reality, we truncate this sum up to some number n. So what we get is an approximation, okay, to this function.